everyone. In this video, we are going to start our chapter on infrared spectroscopy and mass spectrometry. So we have talked about infrared spectroscopy before, but we're going to talk about it in a little more detail and do some review, and then we'll move on to a new analytical method that we're going to discuss called mass spectrometry. It's new to us, not new in general, but here I have a few figures. On the right, I'm showing a traditional mass spectrometer. So this is just a diagram of what's going on inside of the mass spectrometry instrument. Off to the left, I'm showing the instrument that I used when I was doing research in graduate school. There was a company called Waters, and they made a mass spectrometer called a Synapt G2. So this was a little more of an updated instrument, but typically in organic chemistry textbooks, they show you the oldest method. So I'll try to talk a little bit about newer methods of mass spectrometry as well. So here's the instrument diagram for what I used when I was in school. And basically the main difference was instead of a magnet, which we can see in the traditional mass spec, here we use an electric field, and the electric field is generated by these focusing rings. But we'll talk more about that later. Either way, whichever mass spectrometer you use, you end up with a mass spectrum. And you're basically plotting the intensity of a sample of an ion versus its mass to charge ratio. So basically it's mass. But again, we'll talk about this more later on. So let's review infrared spectroscopy. So let's start by talking about light. Remember, light can act as a wave or a particle, and electrons also have this wave-particle duality, we call it. So waves are measured according to their wavelength. So here we have a wave generated from an electric field, and then a wave generated from a magnetic field, and they're 90 degrees apart. So this is what makes up electromagnetic radiation. And again, we measure waves according to their wavelength, which is given the symbol lambda. And this is usually measured in meters, centimeters, or nanometers, depending on how big the wavelength is, or how small, I should say. We can also measure the frequency, which is given the symbol nu. And the frequency tells us how many waves pass through a certain point over a given amount of time. So this is usually given the unit inverse seconds or hertz, Hz. All right, so how are frequency and wavelength related? Well, you might remember that frequency is equal to the speed of light divided by the wavelength. So the speed of light is given the symbol c, and the speed of light is equal to 3 times 10 to the 8th meters per second. Sometimes it's listed as 2.9 times 10 to the 8th. But sometimes we just round up. Now, remember I said that light can act as a wave or a particle. So if we think of the particle-like nature of light, we could identify or measure the energy of that particle. And energy is equal to a constant h times the frequency. Or you could substitute in the expression above for frequency, c over lambda. So h is Planck's constant, And this is equal to 6.626 times 10 to the negative 34th, joules, not meters, times a second. All right. Now, you can have, for instance, a packet of light, also called a photon. And this comes up when we talk about, for instance, the entire electromagnetic spectrum. So here in the electromagnetic spectrum, we have different frequencies or wavelengths of light from lowest energy to highest energy. So notice that wavelength increases going to the left, but energy increases going to the right. So they are inversely related, and that makes sense if we think about the equation for energy, which is Planck's constant times the speed of light over wavelength. So energy is inversely related to wavelength. So looking at this spectrum, we have radio waves, which are the lowest energy wave. And actually, we're going to use radio waves in a future analytical technique called NMR. So that's nuclear magnetic resonance. And this, again, uses radio waves. But we'll talk about that in the next chapter. IR spectroscopy, obviously, will use IR light or waves. So that's a little higher in energy than radio waves. And there's another technique that we've used in the past called UV vis spectroscopy, and this will obviously use UV light and visible light. Okay. So let's talk a little bit more about the energy of light. So you might recall that electrons, if they're excited, can jump from one energy level to another in an atom, and then eventually it will relax back down to a lower energy level, and when it does, it emits a photon, or a packet of light, a packet of energy. So remember that these energy levels are quantized. They're not continuous. So electrons can only exist at certain energy levels. Now, depending on how far an electron jumps and then how far down it relaxes, you can emit different types of light. So you might emit, for instance, blue light or green light or red light. It really just depends on the amount of energy that the photon has. So we can actually do the same thing with bonds between atoms. So if you have, for instance, a bond between two carbon atoms, that can absorb IR frequencies, and that carbon-carbon bond will have its own specific energy compared to, for instance, let's say a carbon-hydrogen bond. Now, when bonds are radiated with IR light, they start to get excited, so they're going to vibrate. And they can vibrate in different ways. So they can either stretch or they can bend. So for instance, off to the side, I have a diagram showing different types of stretching or bending that can occur. So you can have symmetric stretching where your bonds are both going out at the same time and coming in at the same time. You can also have asymmetric stretching where one bond goes out, the other comes in, and then they switch. Or you can have different types of bending. So they could, the two bonds could come in and out, at the same time, or they might both move to the right at the same time and then over to the left. So there's lots of different ways that bonds can move around, or different ways that they're affected by an increase in energy. So that's the same for different functional groups. For instance, if you have a carbon with a double bond to oxygen, that will have its own frequency or stretching movements, or its different vibrations from other bonds. Okay, so that's where IR peaks come from on an IR spectrum. We're just seeing what kind of energy different bonds have. So I also wanted to talk about ways that you can prep a sample for infrared spectroscopy. In our lab at TCC, we do have an IR instrument that kind of looks like the diagram shown here. This instrument has a crystal plate, and ours is made of germanium, but there are crystals that are made of diamond or other materials. So what you would do is, if you have a solid sample, you would place some of your solid on that plate, and then you would use this pressure tower to press down on the solid so that it's kind of squished in between that tower and the plate. And then, of course, IR light is passed through, and then we read what kind of vibrations or frequencies the bonds in the molecule experience. If you have a liquid, you would place the liquid on that same crystal, but instead of using the pressure tower, you would just put a little slide over the liquid so that it spreads out evenly on the crystal. Now you can also use salt plates, depending on the instrument that you have. These salt plates are made of salt, and they're clear, typically, and you would just place your liquid on here, and then you'd place another salt plate on top and just kind of squish the liquid in between those two plates. And then you would place this into your instrument, and then the instrument would pass IR light through it and get a similar reading. If you have a solid, you might need to use these 3 discs here, and you would make what's called a KBr pellet, or a potassium bromide pellet. So what you would do first is you would grind the solid into a fine powder. So you might use a mortar and pestle for that. Then you would mix with KBr. So this just provides a medium for the pellet. And then you would place this disc on the right on top of this disc on the left, and then you'd put your solid in the middle with the KBr. Then you would place this last piece on top, and you would use a device to squish everything together, so you'd apply a lot of pressure, and that would create your potassium bromide pellet. And then you would place that pellet that you made into your instrument, and you would pass IR light through it and do the same thing that we would do with our other similar devices. So there are a lot of different ways that you can prep a sample for IR analysis. All right, so now let's talk about the IR spectrum. And again, this is probably review since we've been doing IR stuff all quarter. But typically, when you run your sample through an IR spectrometer, you're going to get a readout where you have percent transmittance on the y-axis and wave number on the x-axis. Now, wave number is given the symbol nu with a little squiggle on top, and that is equal to 1 over wavelength. Now, part of the reason wave number is really useful is it's proportional to the energy. So if we know the wave number is higher, we know the energy is higher. If the wave number is lower, the energy is lower. So that's really useful. But also notice that the units for wave number are inverse centimeters. Okay, so in an IR spectrum, you might recall that anything above 1500 is considered the diagnostic region. And this is going to give us the most useful information about our functional groups. And then anything below 1500 is considered the fingerprint region. And this is going to give us maybe some information, but it gets pretty noisy at times, so it's hard to really get useful information out of the fingerprint region. All right, so just in general, you can see that from 3200 to 3400, if you have a broad peak, that will indicate an OH stretch. So that is going to tell us we have some sort of alcohol. Now that might be, for instance, a carboxylic acid, but if we had a carboxylic acid, we would also see a stretch somewhere from 1650 to 1800 inverse centimeters. Now that can also apply to ketones and aldehydes and esters. So there's a lot of other groups or functional groups that can apply to as well. Now going back to the left, we can also find nitrogen-hydrogen stretching from about 3300 to 3500 inverse centimeters. You might also see an alkyne stretch depending on your molecule at about 3300 centimeters or inverse centimeters. Now around 2850 to 3100 inverse centimeters is where we'll see other carbon-hydrogen stretching, and where it's exactly positioned depends on whether you have an sp3 hybridized carbon, an sp2 hybridized carbon, or an sp hybridized carbon. So we'll talk a little bit more about that as well. But first, let's talk about Hooke's law. So Hooke's law is generally used to describe a spring and the force that a spring can exert. So we can use this and apply it to the wave number for a bond. So wave number, remember, was given the symbol nu with a little squiggly, and wave number depends on 1, the bond strength between two atoms, and 2, the masses of the atoms sharing the bond. Okay, so Hooke's law tells us that if we have two atoms connected to each other, the wave number is equal to 1 over 2 pi times the speed of light. So essentially that's just a constant. And then we'll multiply that by a force over something called a reduced mass. And then we take the square root of that part of the equation. So the force gives us information about the bond strength. So this is the force constant. So what is the force between those two atoms? And then the mass the reduced mass on the bottom, that is equal to the mass of the first atom times the mass of the second atom divided by the mass of the first atom plus the mass of the second atom. And basically, this is kind of an average of the two masses. So what this really tells us is the greater the mass of the atoms, then the smaller the wave number. So remember, if we go back, we saw the carbon-oxygen stretching at a lower wave number because the oxygen has a higher mass. If we look at, for instance, nitrogen and hydrogen, hydrogen has a really small mass, so we find its wave number to be much larger. And then we have carbon-hydrogen stretching in the 3000 range. That's also kind of towards the left because we have a smaller mass from the hydrogen. So again, if you have larger masses, then you have smaller wave numbers. If you have smaller masses, then you have larger wave numbers. All right, so let's just compare a few bonds. So let's look at a carbon-hydrogen bond, a carbon-oxygen bond, and a carbon-chlorine bond. So the mass of the second atom is increasing as we go across, and the wave number is going to decrease. So a CH bond is found around 3000 inverse centimeters. A CO bond is found around 1100 centimeters, or inverse centimeters, and a carbon-chlorine bond would be found around 700 inverse centimeters. So again, the greater the mass of your atoms, the smaller the wave number. So Hooke's law, even though it typically is used for springs, it can also help describe two atoms bonded together. So it tells us kind of what their force is or how strong their bond is, and then also what the wave number would be based on the mass. All right, so let's talk about the effect of hybridization on wave number. So let's focus on carbon-hydrogen bonds. So we're going to focus on these CH stretches. And let's just draw a few different types of carbons. So let's say we have a carbon that's bonded to hydrogen and 3 alkyl groups. And then let's say we have a carbon bonded to hydrogen with a double bond, and then another alkyl group. And last, let's look at a carbon that's bonded to hydrogen and also has a triple bond with some alkyl group. All right, so what is the hybridization of the first carbon on the left? Well, it's bonded to 4 different things, or potentially the same thing, but 4 different bonds. So it does have an sp3 hybridization. What about this other carbon? Well, it's only bonded to 3 things, so it's sp2. And this last carbon? It's only bonded to 2 things, so it has an sp hybridization. All right, so let's think about what an sp3 orbital looks like. So it has 25% s character and 75% p character. So this hybrid orbital is pretty long, which means that electrons are kind of far away from the nucleus, potentially. An sp2 hybrid orbital is a little shorter just because it has more s character, has about 33% s character. And then an sp orbital, it has 50% s character, so that's going to be more spherical. So electrons will be closer to the nucleus. So which carbon-hydrogen bond is the strongest? So another question, which one is the shortest? So the sp hybridized carbon will have the shortest bond with hydrogen due to its sp hybrid orbital. So that will also be the strongest CH bond. Now on the opposite end, we have our sp3 hybrid orbital. That will have the longest CH bond. So it's also the weakest CH bond out of these three. So that's going to correlate with the energy of the bonds. Okay, so remember that energy, we said, was equal to Planck's constant times the speed of light over lambda, the wavelength. And then we said that the wave number was equal to 1 over wavelength. So that tells us that energy is equal to Planck's constant times the speed of light times the wave number. So we just plug that in for 1 over lambda. And really, we can just say that energy is proportional to the wave number. So the higher the wave number, the higher the energy of the bond. The lower the wave number, the lower the energy of the bond. So if we look at the sp3 hybrid carbon-hydrogen bond, that will have a lower wave number or lower energy. So that will be found at less than 3,000 inverse centimeters. So we'll put low energy there. So it doesn't take a lot of energy to break that carbon-hydrogen bond, for instance. But then if we go all the way over to the sp hybridized carbon, that carbon-hydrogen bond is really strong. So it would take a lot of energy to break that carbon-hydrogen bond. So that means its wave number will be much higher at about 3,300 inverse centimeters. And then the sp2 hybridized carbon is somewhere in the middle. It's typically found a little bit higher than 3,000 inverse centimeters. So that's our sp2, and it's in between the sp3 and sp. So when you're trying to identify what type of carbon-hydrogen bond you have, you do want to think about hybridization. So if you find that you have an alkyne stretch, or sorry, a carbon-hydrogen stretch around 3,300 inverse centimeters, you know that you probably have an sp hybridized carbon. If you have a stretch at a little less than 3,000 inverse centimeters, that tells you you have an sp3 hybridized carbon, so it likely has all single bonds. And then if you have something a little bit higher than 3,000 inverse centimeters, that likely is an sp2 hybridized carbon with a double bond, but additionally it's still bonded to that hydrogen there. All right, so hybridization can have a big effect on where your peaks show up. And that can help you further identify what type of functional group you have. Do you have single bonds, double bonds, or triple bonds? Okay, so let's look at the effects of hydrogen bonding as well. So let's say that we're looking at ethanol. And we know that if hydrogen is bonded to oxygen, nitrogen, or fluorine, it can potentially go through hydrogen bonding as long as there's another electronegative atom nearby. So let's say we have another ethanol molecule. That's going to create a hydrogen bond. All right. Now, when a hydrogen can form a hydrogen bond, that actually weakens the original bond that hydrogen has. Now, not all of the ethanol molecules in a sample will go through hydrogen bonding. Some might just kind of hang out on their own. Some might have multiple hydrogen bonds. It kind of depends on your molecule and how it's set up. So you might end up with a distribution of hydrogen bonds. So for instance, some molecules might have multiple hydrogen bonds. Oops. Multiple H bonds. Some might only have one or none, etc. So that's what broadens that OH peak that we've talked about before. So if you have a really skinny OH peak, that is going to indicate that you don't have a lot of hydrogen bonding occurring, and we call this a free OH stretch. But if you have a really broad peak, that will tell you that you have a lot of hydrogen bonding. So that can also help you kind of narrow down what type of molecule you have. So for instance, if you have a carboxylic acid, let's see if I can draw this off to the side. Not only do you have this OH group here that can go through hydrogen bonding, but you also have this oxygen that could hydrogen bond, for instance, with another molecule that has an OH group. So that's going to really broaden this OH peak here. So just something to keep in mind. And then let's also talk about amines. So remember, amines contain a nitrogen. So you could have what's called a primary amine, where the nitrogen is only bonded to one carbon group. Or you could have a secondary amine, where the nitrogen is bonded to two carbon groups. So we said that nitrogen-hydrogen stretching occurs in this region, so sort of around 3,500 to maybe 3,300, and sometimes that peak can show up like vampire fangs, which is kind of fun. Now, if you see these vampire fangs, you'll know you have a primary amine. Okay, so why is that? Well, this has to do with that symmetric versus asymmetric stretching. So if you have a nitrogen with two hydrogens, they can either stretch symmetrically or asymmetrically. So half of the amine molecules in your sample might be stretching symmetrically, the other half might stretch asymmetrically, and that's going to give different frequencies or different wave numbers. So these vampire fangs are due to that symmetric and asymmetric stretching. Now, if you have a secondary amine, you're only going to see one peak. In that same region. So because that nitrogen is only bonded to one hydrogen, you're only going to see one peak there. Okay, so I think that's all we're going to cover for IR spectroscopy. Hopefully this was really good review. I know you've already been identifying IR spectra, and you've been labeling peaks, but we dove a little bit deeper and talked about why sp3 hybridized carbon-hydrogen bonds are lower in wave number versus sp hybridized carbon-hydrogen bonds. And then we also talked about the effect of hydrogen bonding on the OH peak, as well as amines and how their peaks look depending on how many hydrogens they're bonded to. All right, so in the next video, we're going to talk about mass spectrometry, and we're just going to kind of introduce the topic and then we'll go into more detail. But I also wanted to let you know about a worksheet I posted where you can gain more practice with IR spectra. So that is called the IR spectroscopy worksheet. And it's a pretty long worksheet, but it's going to give you a lot of practice trying to identify compounds given the molecular formula of the compound and its IR spectrum. And then the key is also posted. Additionally, I posted a video under modules week 7. You can also find it under Panopto Recordings additional videos. And this video just goes over the first 2 IR spectra on the worksheet and how you can identify a molecule and its functional groups as well as its structure. So if you need a little help getting started, that video is available. All right, so I will see you in the next video when we'll talk about mass spectrometry.